Hi, my name is Abbie Martinez, and this is my Lab 3 lab report. Introduction. So the purpose of part 1 was to determine the mass of a black hole based on the motion of a star orbiting the black hole. The purpose of part 2 was to determine the initial velocity of a spaceship such that it can be close enough to the black hole without crashing and still be able to leave the system. Fundamental physics principles. Newton's second law allows us to derive velocity update and position update as seen on the left. Newton's second law also allows us to derive dp dt through the following derivation steps indicated on the top right of the screen. We all use delta p equals mass times delta v to give us two individual momentum equations we later use in the glow script code for part 1. The universal gravitational force allows us to manipulate the equation for magnitude of F net seen on the bottom right to solve for the mass of the black hole. Here's a brief preview of the main results. The mass of the black hole was averaged to equal 1.38 times 10 to the negative 4 kilograms, and the initial velocity of the spaceship in part 2 was negative 2 times 10 to the 7, 9 times 10 to the 6, 0 meters per second. Models with description. Here's the model generated. GlowScript model part 1. The system was a black hole and the surrounding was a star. The initial conditions included the universal gravitational constant, as well as the mass of the star, delta t, and the time of first observation. The code on the right illustrates how for every index and position, we calculate delta x and delta y in lines 136 and 139 respectively, to then get the change in velocity for both directions. These values are stored in a list that we then use for computing momentum. The derivations highlighted in green on previous slides are now seen here in the code. We determine initial momentum and final momentum in lines 163 to 164, and then use that to get delta P in line 168. We also use the same process with velocity. Newton's second law is directly seen in line 171 and 174. The highlighted equations on the bottom right are seen in lines 177 and 179 that calculate the change in momentum over time using the perpendicular and parallel components. Line 192 illustrates how the magnitude of the universal gravitational force was manipulated to yield the mass of the black hole. GlowScript model part 2. The system was a spaceship and the surrounding included the black hole and the planet. Initial conditions here are the mass of the black hole from part 1. Other constants are listed on the right. Bottom image illustrates how our guess and check initial speed values for the planet and spaceship like escaping the system. The format for lines 76 and 77 are essentially repeated in sets circled on the left. This follows the force of gravity vector equation on the right in blue. The update position and update velocity equations are also used on the bottom left image for both the planet and the ship. Discussion and results. The blue arrow gives us F net parallel, the pink arrow gives us F net perpendicular, the orange arrow gives us F net, which is the sum of those components. The mass of the black hole was 1.38 times 10 to the negative 4 kilograms. For part 2, the magenta is the ship's trajectory, while the blue is the planet's orbit. The ship escapes the system and gets close to the black hole using the initial velocity vector highlighted in yellow here. The ship is moving left and upward. Possible sources of error included that the mass of the black hole was averaged and not a constant value. Running this for a longer time would increase accuracy since it would yield a more accurate average. In part 2, we use guess and check to find an approximate initial velocity of the ship. This leads to a large range of human error. Conclusion. What does it mean? Fnet is the sum of all forces acting on the object. Here, the perpendicular and parallel components are easy to observe with arrows, but not measure. Rate of change in momentum describes this force as at one particular instance. Here we can use an interval of time, mass, and change in velocity to easily observe and calculate these components. That is the difference between these two. For part 2, what if? The ship's trajectory formed an orbit similar to the planet's when the initial velocity of the ship was changed to negative 3 times 10 to the 6, 9.6 times 10 to the 6, 0 meters per second. And here you can see that the ship's trajectory is slightly lower in initial velocity than the planet's initial velocity.